Okay, this is the Physics Chapter 8 Lecture 1 video. Open up your books to page 252. That'll be the first figure that we look at. And have your notes out. Please let me know if you're unable to print out these notes. I uploaded it in a Microsoft Word document, but if I need to change that to a PDF, if it's not printing out properly for you, just let me know. Okay, so energy is the ability to do work. Work is the product of the displacement and the component of the force parallel to displacement. So if you were to look at this diagram of this little boy pulling a wagon, the work is the force parallel to the displacement. So the displacement is going to the right. The only force that counts towards the work is the x direction force. Okay, so everything in the y direction is wasted in terms of calculating work. All right, definitely worth reading that excerpt there. Okay, so the work equation, all right, this one you'll end up memorizing. Work is equal to the force parallel to the motion times the displacement, delta x. The unit is Newton meters, and that is the same thing as a joule. All right, so you'll be using joule. So let's look at 8.1. Right, so this is on page 254. So it says a gardener is expanding her garden. In order to do this, she must push a heavy rock out of the way. She pushes the rock straight in the direction that it travels, moving 451 centimeters. We'll need to convert that to meters. If she does a total of 34.5 joules of work, how much force did she apply? All right, so this is just an algebra question. So if you have work is equal to force parallel times displacement, you want to solve for force. That's just going to be work divided by displacement. So it says the work is 34.5 joules. The displacement is 451 centimeters. That's 4.51 meters. So you stick that in the old calculator and you get 7.65. And the unit for force is newtons. Okay, so going back to maybe middle school science, you probably talked about this potential energy. I know we did in chemistry also a little bit. Stored energy, but it's not in motion. So the potential energy equation, so you'll need to memorize this and you'll use it a lot. Potential energy is mass times gravity times height. All right, mgh. Okay, the unit for that also joules. Okay, kinetic energy, that's energy in motion, and that equation is 1/2 mass times velocity squared. All right, so you know it's going to have motion in it because we have a velocity. Okay, so you'll need to memorize those two. And I don't know if I have room to work 8.2 underneath here, so I'm going to erase. Pause the video if you need to. Let's rewrite these equations. Potential energy is equal to 1/2, no it's not, sorry, mgh, and kinetic energy equal to 1/2 mv squared. So 8.2 is on the top of page 257. So it says a roller coaster car is at the top of the highest hill on the track. If the potential energy is 7.72 times 10 to the 5th joules relative to the ground, 6.67 times 10 to the 4th joules relative to the next hill the car encounters, what are the heights of the two hills? Okay, so this problem is illustrating that Potential energy, that height is relative to whatever position that you are analyzing. Okay, so let's draw this roller coaster out. Okay, so let's say it's just an old-fashioned roller coaster like that. Here's the ground, and these are the cross members. All right, I grew up with an old roller coaster called the Pippin that looked a lot like this, up and down and up and down and up and down. It had all these wood supports. It didn't have the metal tracks that they have now. And so the height from the top hill relative to the ground, let's call that H1. And then the height at the top of the second hill to the ground, let's call that H2. And then the distance between the top hill and the top of the second hill, let's call that H3, right? So I did a little, it's smashed in there a little bit, but that's H3. Okay, so the first part of the question says, if the potential energy is 7.72 times 10 to the 5th relative to the ground, what are the heights of the two hills? Well, relative to the ground, you would have H1. So potential energy is equal to mass times gravity times H1. Okay, so let's figure out H1. So H1 is going to be potential energy over mass times gravity. So that'd be 7.72 times 10 to the 5th. The mass of the car is 365 kilograms. And then, of course, 9.8. So the height of Hill 1 is 215.8 meters. All right, that's not what it's asking. Well, that gives you Hill 1. Okay, so that's H1. That's one of the answers. It also wants H2, but we weren't given information concerning the potential energy from this hill to the ground, but we were given enough information about the potential energy between H1 and H3. So the second potential energy is mgh3, okay, because it says the potential energy relative to the ground and relative to the next hill. Okay, so that would be this distance. So H3 is equal to potential energy over mg. And it says the potential energy is 6.67 times 10 to the 4th. And then you still have 365 kilograms, same denominator, 9.8 meters per second squared. And that is, H3 is 18.65. So if you want to get H2, it's going to be H1 minus H3. So that's 215.8 meters minus 18.65 meters. So the height of the second hill, all right, relative to the ground, is 197.2 meters. All right, pause the video if you need to. Let's look at 8.3 at the bottom of 257. It says the engines of a rocket ship give the ship a kinetic energy of 4.5 times 10 to the 10th joules. How fast is it traveling? So kinetic energy we know is 1/2 mv squared. So solving for v, it's going to be the square root of the kinetic energy divided by 1/2 of the mass. All right, so that's going to be the square root. It says the kinetic energy is 4.5 times 10 to the 10th. And we have 1/2 of the mass, 1.34 times 10 to the 4th. Cougs. All right, place that in your calculator and get 2592 meters per second. Dun, dun, dun. All right, those are kind of plug and chug type problems. And we have a couple of, the next two problems are a little more interesting. So pause the video if you need to. I'll leave these two equations up here. So we're on page 2 of the notes. We're going to go to the bottom of page 2 and that'll be it. The first law of thermodynamics is energy cannot be created or destroyed. It can only change form. So what that means is that total energy before has to equal total energy after. So no matter what change in the situation you have, a change in height, a change in speed, first law of thermodynamics says that the before energy will equal the after energy. Okay, so the energy equation, the overall one, is total energy is equal to potential energy plus kinetic energy. All right, let's look at 8.4. Okay, a lot of blue pages to look past. Okay, so 8.4 says a biker pedals hard to ride his bike to the top of a 21-meter hill. He rests momentarily at the top, exhausted. So right here, the biker stops moving for a second. He then decides to let his bike coast down the hill. That's important. He's not adding energy through pedaling so that he doesn't have to pedal. He is having so much fun coasting that he decides not to pedal even when the bike begins climbing the next hill. If the hill is 12 meters high, so the second hill is 12 meters high, what will the biker speed be at the top of that hill? And we get to ignore friction, which is helpful. Okay, so the way we have to analyze it, we know that the total energy at the first hill is equal to the total energy at the second hill. All right, so let's say, we'll say that's potential energy, first hill, plus kinetic energy, the first hill, has to equal the potential energy of the second hill, plus the kinetic energy of the second hill. Okay, the first hill we do have height, right? It's 21 meters, but he stopped, so we have no kinetic energy. At the second hill, though, we have both. We have both height and the bike is moving. So that's going to be mg hill 1 is equal to mass times gravity hill 2 plus 1/2 mv squared. Now notice every single equation has mass in it. If all three equations have it, all right, all three terms have it, you can get rid of it. Now if it were missing out of one of them, you couldn't. So I'd have g times hill 1 is equal to the gravity times hill 2. See, we can't get rid of gravity because you don't have any gravity in this last equation. Okay, so that's going to be 9.8 times hill 1, 21 meters, is equal to 9.8 times hill 2, which is 12 meters, plus 1/2 times the velocity squared. All right, those numbers, let's dispense with the units for a second. So this would be 203 5.8 is equal to 117.6. That's 9.8 times 12. Plus 1/2 v squared. So I would have subtract 117.6. 88.2 is equal to 1/2 v squared. So the velocity is going to be the square root, if I flip and multiply that 1/2 of 2 times 88.2. All right, and that is 13.28 meters per second. All right, pause the video if you need to. And got one more to work. Okay, this is 8.5. Okay, so here we have a teenager shoots a target with his BB gun. Target is mounted on a post so that it's 25 meters higher than the tip of the gun. Okay, so they didn't give us the height of the tip of the gun to the ground, but that's okay. We're going to assume that that height is height 0. That's ground 0 right there. Okay, and you couldn't plug in a number anyway because they didn't give it to you. So that's height 0. This would be height 25 at the target. If the gun shoots the BB with an initial speed of 99 meters a second, at what speed does the BB hit the target? And we want to ignore air resistance. Okay, so we would have the total energy at the barrel, right? The tip of the barrel. We'll say the tip has to equal the total energy at the target. So that's going to be the potential energy. We'll call it, at tip we'll say, we'll call it 1 and 2. Potential energy 1 plus kinetic energy 1 is equal to potential energy 2 plus kinetic energy 2. All right, so that's potential energy 1. Remember, we said that the barrel, the tip of the barrel was at height 0. So that makes that 0. And then we have some height here. However, but we're trying to get the kinetic energy of the second so we can get the velocity. So we have 1/2 m times v1 squared is equal to mg h2. Or so the height of the target plus 1/2 m v2 squared. Okay, so all of our masses are going to cancel since we have mass in every single one. So that's 1/2 times 99 meters a second where it started, squared, is equal to 9.8 times 25 meters, right? That's the height of the target, plus 1/2 the second velocity squared, which is what we're trying to get. Okay, so that's going to be 4,900.5, if you multiply that out, is equal to 245, that's 9.8 times 25, plus 1/2 v2, and don't forget to square it. Okay, so subtracting 245, you would have 4655.5 is equal to 1/2 v2 squared. So v2 is equal to the square root. When I flip that 1/2 and multiply 2 times 4655.5, and you have 96.49 meters per second. That makes sense. You would expect it to slow down a little bit, right? It gained high energy height, but so it's going to have to slow down. There's not a motor on the thing, so it'll slow down on the way to the target, but not much. So that does it for this lecture. The homework tied to this lecture would be review questions, page 284. You can do 1 through 6, and practice problems, page 285. You can do 1 through 5. All right, so I will talk to you next video.